Good morning and good afternoon to everyone. Welcome to today's AI for Hybrid Electronics webinar series hosted by Nextflex. Today's talk will be on closing the loop, AI-driven predictive modeling for printed electronics. I'm Scott Miller, Director of Technology at Nextflex. Before we move to the presentation itself, I wanted to give some background on this series. This is I believe, the fourth webinar we're hosting in this AI for Hybrid Electronics series. Open to both Nextflex members and non-members to discuss key opportunities related to AI for the field. We have spent much of the last year looking at what the opportunities in this space are, and we've identified a number of different ways that AI will impact hybrid electronics and that hybrid electronics will also impact AI. Things such as boosting design and manufacturing efficiency, enabling smarter adaptive devices, and strengthening U.S. industrial base resilience. So we encourage you to look back at some of the previous webinars that are all available to you online, and reach out to us with any questions and topics you'd like to discuss. We are in the process of developing an AI for hybrid electronics roadmap. This is something we started late last summer and are taking input from the entire industrial base, all of our industry and academic members, and certainly non-members in this space as well, looking to really lay out what is the scope, what's the background and current state of the art, all the way through the vision and objectives and the technical gaps and challenges, leading to an outlook for the field. We will be using this to guide future Nextflex investment and hopefully also align the investment of our partners on the government side as well as our partners in the private industry side. So certainly encourage your participation in that process. For those of you who don't know Nextflex and why we would take on this kind of opportunity, Nextflex is the Manufacturing Innovation Institute for Hybrid Electronics. We are partially sponsored by the Department of Defense and have a large collection of over 200 industry, academic, and government member organizations that we work with a common mission to strengthen the U.S. industrial base for electronics manufacturing. We do that through a three-pillar mission: advancing the technology and manufacturing, strengthening and growing the industrial base, and securing human capital, are part of our workforce and education mission. We do this through a number of different activities. We have our consortium that I've mentioned. We have technical working groups that look at what is the future of the technology and manufacturing in 11 different areas. We fund projects. Project calls to date, more than $145 million over the last 11 years. And we have a project call that's now closed and in selection phase right now. That'll be our 11th. We do a lot of information dissemination, workshops, webinars, events such as this, as well as our annual member meeting, which is coming up in a few weeks. Our education and workforce development programs and our technology hub, where we are part of the industrial base as well as a convener. Last few things before we jump into the webinar itself: upcoming events. For Nextflex members, we have 5 project call webinars scheduled for the month of June. These are Nextflex member benefits to participate and attend these and hear about the work that's going on in the funded projects. If you are interested in receiving the invitations and you don't already get them, you can contact Eliana Schoenberg. Her email address is on the screen. She'll add you to the distribution list. Innovation Days, I mentioned. Our annual member meeting is coming up the week of June 9th to 11th. Be held in person in Mountain View, California. And we're really excited that this year we are hosting it in conjunction with the TechBlock Future of Electronics Reshaped Conference. We'll have technical presentations. We'll have member-only sessions, both as part of Innovation Day and as part of the TechBlock Conference, as well as plenty of networking opportunity. There's a QR code on the screen right now, which is registration and information about Innovation Days. We're actually giving a discount for today only, 20% off registration. So if you're interested and have not yet attended, please jump in and register. And also be aware that registration for the TechBlock Conference is a separate registration. So if you've registered for one but not the other and you mean to go to both, that is something to take care of. All right, last announcement. We're very excited to be hosting a Defense Patent Holiday event, July 14th and 15th in San Jose at our facility. This is an opportunity that we are hosting in conjunction with the Department of War, the Manufacturing Technology Program, as well as the Technology Transition and Commercial Partnership Program in the Department of War. So This is an opportunity for members of the industrial base to get access to the large patent portfolio of DoD lab developed technologies and potentially expanding that out into others for the purpose of bringing them to fruition. So please join us to learn more about that. All right, it's now my pleasure to introduce today's speaker, Professor Ben Davaji from Northeastern University. He is going to be speaking on closing the loop, AI-driven predictive modeling for printed electronics. Ben has been doing work in the area of AI applied to electronics manufacturing for a number of years, going back through his PhD work in electrical and computer engineering at Cornell and at Marquette, and his postdoctoral studies at Cornell University. Ben, I'll hand over to you.
Thank you so much. Let me figure out the sharing screen. Can you see my screen?
We can see it. Looks great.
Thank you for having me here, and hi everyone. It's a pleasure to share some of the results that we have, and here I'm going to discuss our progress and some ideas. I'm with College of Engineering at Northeastern, Boston, and also I'm a member of the Institute for Nanosystem Innovation, NanoSI. I started my own lab in 2022, so it's kind of a new lab. So when you have a new lab, a lot of your data is still overlapping with the data and work that I did during my postdoc at Cornell University, and now new work that we are doing at Northeastern. We still collaborate very closely with the team at Northeastern, team at Cornell, and a lot of result will be a broader Cornell and Northeastern team. Let me start by acknowledgement. Professor Amit Lal and Peter Dorshak at Cornell are the main PIs when we started this work for semiconductors, and then basically continued to the printed electronic. Thanks to a lot of contributors from both Cornell and Northeastern team, most importantly, Master of Engineering team at Cornell over the years. We have gotten support from so many companies, so if I miss any, please just forgive me, but Nano Dimension, Volterra, Giga, ACI Material, and Nanotronics are direct supporter of us. We have received a lot of support. Probably the idea of this work kind of initiated by FlexTech program manager Geeti Samedi and her broader team, and also we have received a lot of support from a Smart Data AI initiative within SEMI. The origin of this work goes back a little bit to a program in DSO office at DARPA. Basically, Ted Senator was a program manager. He was interested to see interaction between physics and AI. He did not particularly have the emphasis on what problem are you solving. He just wanted to see where are the efficiencies in interaction between AI and data. We were lucky. Professor Dorshak wrote a proposal, and we get the chance to play with some toys. Some of this work has been funded and supported by FlexTech program, and here's the acknowledgement. All of the material I'm going to use today is the published material. They are fully available online for access, and if you need any more information, I'm happy to provide. So I'm not an expert in developing AI algorithms, and also I'm not expert in printed electronics. So what am I doing here? We are very interested in learning how to use AI to solve some of the device and fabrication problems, and also maybe at the beginning for a wrong reason, I got interested in printed electronics and FHE, but now things has been changed in that. I'm going to share the story with you. Here, my idea today for this webinar is if I share tools and examples that we have developed and some ideas on how to implement them. I would love to get inputs from the community, broader community, that where are the sweet spots to implement and where we are doing it maybe suboptimal that we need to add some touches. I will start with an example from semiconductor, discuss about the FHE data, and then we'll open up some predictive models and examples and continue with possibilities and wrap up with some high-level considerations that probably each one is the topic of its own. So I'm a MEMS person, so my focus in my lab, the main focus is developing MEMS and piezoelectric MEMS. We develop gigahertz ultrasound devices for biointerface. We also try to push computation closer and closer to sensors, so we integrate them together, so that helps with time, energy, and also implementing the edge compute process. A part of my lab, an effort works on focusing on developing AI-based digital twins for processes that supports making devices for first to trust, but also we have accidentally we have this trust that's additive manufacturing in my lab. It's a very welcome accident at this point, and I will explain more. So let me start by saying a few things about AI. Nowadays, you can't be in a room and don't talk about AI. This was said by in multiple meetings in the last few weeks, and that's kind of true. It's in all aspects of our life. But if the simplest and most easiest definition for AI and machine learning is learning from examples. If we have enough examples, we could learn trends, we could learn fitting, we could learn the behavior and extract that and use it. Usually, even it's not discussed in this, but implementation requires 3 phases. In phase 1, you have to train a model. This is almost like you have a data, you have a labels, and in this case, it's supervised, but of course, they are more unsupervised implementations are possible. The second phase is testing and validating. Is trainings are converged? Is the model validated? So train and test is usually sometimes combined together as a training, but we also always need to test the training results. And the last is use case. Sometimes we call it inference, but this use case is when you have a trained model, and as long as your models are validated, you could use a data to learn the outcome or predict the outcome. This is basically data and labels and tracking. Those are very, very important, and the accuracy of models usually traces back to the accuracy of labels in case of the supervised case, and also the uncertainties within measured data. So sometimes if the example data does not match the use data, more complex transformations are needed. I'm trying to going forward with touching some of this in my presentations. In general, machine learning and AI has been around for decades, at least 60, 70 years, and has been recently gone through a lot of advancement. Most of it is due to the algorithmic advancement and availability of large data sets, and also complemented by computational resources. We have a large clouds and HPCs. We have accelerators like GPUs, TPUs, and every day a new version being added to the arsenal. AI has been very successfully implemented in e-commerce, like stock market, face recognition, and driverless vehicles, and also has been used for material science. For example, discovery is one of very interesting recent scientific fields. In terms of the electronics, is mostly and kind of AI is used to apply to the outcome of the electronics, sometimes for computation or pattern recognition within the IoT sensors or edge devices. Application of AI in micro nanofab and printed electronics are mostly exploratory. So the real quantified and verified applications is at early stages, but this is believed to be because of interest is a very rapidly evolving phase. Also, we have been hearing about digital twins. So digital twins are usually models that connects a real-world object or process to a model. Sometimes these models are physics-based, sometimes they are AI-based, but the one difference between these type of modeling and a traditional modeling that probably all of us know from engineering courses are these models needs to be updated regularly, and they call it a live link, where between a virtual object and the real object there should be a continuous connections. In general, it's possible to generalize a digital twin or AI model for representing a real object, but in practice, I think it's more likely that we focus on targeted domain-specific AI models or digital twins because it's just too expensive to develop a generalized enough digital twins that covers all aspects. And I will give more examples. But digital twin has been recognized by National Academic as a research gap, foundational research gap, and some definition and some specific criteria has been identified. Even though there is not full consensus, this is an evolving field, no definition is guaranteed to stay. And also, NSF has recently identified this as a tool to solve a big problem or difficult and complex problems. Under the hood, these models, these digital twins, could be completely based on physics and first principles, and it could be completely based on data, means that sometimes we call it a black box. But looking more closely, I personally prefer first principle modeling because it's accurate, it's quantitative, you can extrapolate, but the downside of these models are sometimes it's computationally expensive, or sometimes we are dealing with a multi-physics, scales are different, you are looking at large features in microns and roughnesses in nanometers. That's a very different physics if you want to learn to predict everything in printed layer and trace. So not having access to the full physics is sometimes a reason that there are limits within the first principle modeling, and also not having exact boundary conditions. If you are printing multi-layer on top of each other and the interaction between layers matters, we don't have a good access to that boundary condition, or even we have meshing becomes so small that computationally it becomes very difficult. In the other side, we have a data-based models where they learn the process, they learn material, they learn device because they are extracting outcomes and trends directly from data. But the problem with them is it's as good as the data you have, means that if you train within a neighborhood, you can interpolate. Extrapolation is proven difficult and maybe sometimes impossible. Also, one critical difference between these two, first principle modeling can get some statistical ideas about noise processes within the data, but with the data-driven models, they are a little bit limited. Just imagine if you want to learn the noise, white noise from data, you need infinite number of examples. In best case, a combination of these two probably will be the better implementation to deal with different problem at different scales. So hybrid digital twins and hybrid AI models that have some sense of physics could be a better kind of implementation. So let's look at a few examples. Before jumping into the examples, the way we got into this was we were making semiconductor-based and MEMS-based devices, and we start looking into the developing AI models that can learn the process. And later, Giti had this idea that can we apply this to printed electronics? And we thought, yes, but I learned that they are kind of a strategic and also systematic differences between two ecosystems. Semiconductor manufacturing ecosystem is a batch processing. It's very complex. It has so many methods, but It has a mature standards. It has developing standards for material, for EDA, for testing, for equipment data processing, for many, many things. And it's continuous, very development has a multiple generation and versions of the standards. So when we want to deal with the data and specifically between the steps, there are clear pathways. It has a commercial, very strong commercial ecosystem of the EDAs and TCADs and also commercially developed PDKs. It uses automation and automation for many, many testing methodology, in situ monitoring commonly. So getting data out is not a problem. Even I say that sharing a data is a very, very big problem. We will come back to that later. But also, often the designer is not manufacturer, even in the IDM cases that they have the full design house and the manufacturing owned by one entity. Usually these are physically and also kind of structurally very far from each other. So a lot of these standards are designed to bridge those gaps. There has been a lot of investment in developing more and more advanced nodes, but I just wanted to show you this, that a lot of this increase in the cost is coming from software. So the software expenses are skyrocketing exponentially, and you can see that start becoming a dominant part of the cost of technology. And digital twin and AI actually fits somewhere within those blocks. In terms of the electronic ecosystem or FHE ecosystem, I was looking for a similar chart, but what I learned was there are so many different technologies, and there is no kind of natural selection for what's the main kind of a winner in this technology. For example, we have been looking into the printing electronic by inkjet or extrusion, but I have gotten some inputs from different presentations that those are more R&D. Manufacturing is more screen printing, but each one has a kind of a specific use cases. All I learned is, again, I'm happy to be corrected, that there is no consensus on what technology is good for what, at least something that I could clearly understood. So one, in contrast to semiconductor manufacturing, we have a batch processing possible, but usually in manufacturing settings, not in R&D. Even within manufacturing settings, standards are available and developing, but not touching every aspects. For example, the equipment data or basically in situ measurement data is not really touched, but some of the material and substrate and ink, there are some developing standards, some reliability standards. So a lot going on, but it's kind of a little bit behind compared to the semiconductors. Maybe it wasn't needed at the beginning. The design ecosystem is not mature. Definitely, the requirements are also sometimes more complex because you need to deal with ECADs and MCADs and how they evolve together. The other thing is, the other aspect of here is the automation of the metrology and measurements are possible. Again, all of those tools are manufacturing tools, not real R&D tools. So a lot of development actually stays in manual measurement, which is a problem for data. Something that I learned also, a lot of times, in contrast to semiconductor, R&D, specifically in R&D FHE, usually designer is the manufacturer or a close to manufacturer, or somehow there are closer collaboration. Here are a few technologies that our brother team, Northeastern Cornell, we had access to. And the reason I would like to show this to you is I wanted to show you some examples, but please see those examples from narrow vision of somebody who's just learning how things work. We started with a simple printer. We get access to more complex printer. Each one has a different requirement. Each one has a different capabilities, and they use different technologies. But what I learned is This is a tiny example of what's available out there. And there are so many different kind of technologies and inks. So when we want to apply AI, that's why it's very hard to claim a generalization. Even there is a good idea, it needs to be tuned and trimmed to requirement of the exact process, exact material, and exact substrate. In some time, that kind of gives me a feeling that it's not straightforward developing one AI and deploying it. Rather, you need to redevelop it to a small extent for each of implementations practically. Let's start with an example. This is the next kind of part of the presentation. We started with looking into the lithography processes. The good example here is if you look at the aerial images and the maps, they look like layouts and what's on a wafer or what's printed. So we used similar type algorithms. These are the conditional generative adversarial networks that used for domain translation. They connect two different domains that they have different features. And we try to implement that for lithography process. At Cornell, we had access to the deep UV lithography. We collaborated with Hitachi for automated measurements, and we learned translation between a binary layout to SEM images. So the top image is actually experimental image. You can see that there are some rounding of edges, some roughnesses of resist, and some imaging artifacts. And these are the part of the real experimental data, but in the AI predicted world, you don't need to go to the clean room. You can just use a trained models that learns to predict the outcomes. The feature details are extremely accurate. The dimensions are very, very accurate. I'm going to share some quantification on that. We have expanded this to different type of the layouts and mostly to support our MEMS device fabrication. We have done more complex processes. Here is the etch process. Just very quickly, these processes are more complex. They have a sidewall, they have a micro trenching, but same methods, image translation can learn some of those. Now, last thing on semiconductor that I want to share is not just you learn translation, but you can add process. For example, in case of the positive resist, you can have a process parameters to be tuned, and you can see for a same input, same layout, the outputs start differing when you expose the resist with different doses. And actually, the digital twin exactly learns that. Bringing to everybody's attention, all of these images are 2 micron by 2 micron, and my pixel size is around 4 nanometer per pixel. So we are within the limitation of the measurement. And you can see the trends are very accurate. This can be done for more complex processes like etch, where you can compare the real and AI generated images, and you can see we learn very well. So we were doing this research, and we got the idea, can we use similar methods for printed electronics and FHE? I'm going to share a couple of examples on this, and maybe after that we could brainstorm that what can be done better, or if there are other use cases for these models. So in first example, I want to create a printer digital twin, AI-based digital twin. I want it to be process aware, and I want it to learn to predict the outcome. If I give a layout, give a recipe, it tells me what's the outcome. To get there, we had to create a data set. We had to use a specific ink. We have to use a specific substrate and some recipes, and start collecting data. This is a workflow that shows that we are collecting optical data, we are collecting electrical data, because I don't want to just see how devices look. I just want to measure sheet resistance or overall kind of a resistance of a structure. We used Dragonfly from Nano Dimension, and we start printing large data sets. These are the DOEs that intended for machine learning. Something that I wanted to say is, a lot of times when you design a DOE for process development, the DOE is designed to really tighten the process window, and you want to get a tight control, understand where the operation points are. With machine learning and AI, we wanted to have a different design of a DOE mentality in place, because you wanted to see where the process window start changing the behavior. For example, where is the optimum, where things are getting worse. It means that smaller than certain size or larger than certain size, and you wanted to capture some of those trends to complete the learning. So there are some sophistication within the designing of these DOEs for machine learning. We started using different type of devices. We have developed resistors. These are 4-point probes on the left. We have developed a multi-layer where both conductive and dielectric and another conductive layer ink capacitor, parallel plate capacitors in a GSG structure, and coplanar waveguide. So each one has a specific reason. We wanted to learn resistivity, we wanted to learn multi-layer, and we wanted to learn something that has a not only DC value, but it has spectrally interesting features. To do that, after we create a data set, we wanted to automate the measurement of the data. One problem, again, being in R&D setting or academic settings, we don't have all the right tools that can measure a lot of data at this scale. Devices are big for the field of view of the semiconductor metrology kind of tools, certainly big for SEMs, but at the same time, you wanted to mirror a lot of them, and that's a problem. And we used a very simple solution. The way we are printing papers and collecting images, we bought the most expensive scanner that we could find on Amazon, and we ordered it, and it has like almost 1,000 times worse resolution compared to the SEM, but it works pretty well for structures that we were intending. Here we are looking at the 150 to 600 micron lines. I totally understand for some of the more high-end, especially the kind of a jetted traces, this might be not enough, but for inkjet, this was working pretty well. So the workflow still has two steps. We have a training and test, and we have a use case. In training phase, we have two models that in a game theory type configuration go against each other. There is a generator and there is a discriminator. Generator starts from the white noise, start guessing, and it gets corrected by discriminator. This continues all the way to generator learns how to guess the right outcome for given input. Then when we have a trained model, we can use it to predict the outcomes. Here are some results that I would like to share. If we start changing the recipe parameters, for example, the tray temperature or dynamic top oven speed, this is a parameter in this printer. I know different printers has very different parameters, but here 0 means it's off, 200 means the hottest because it moves slowly, and 400 means moderate temperature. So basically, this is how different process parameters impact. And we could start looking at the sizes of the width and gap, and this is a mean average error for what we are predicting. So you can see our prediction accuracy is within single digit, sometimes less than 20 micron for 150 micron structures, and each side of this violin plot shows width measurement versus gap measurement, and you can see similar accuracies. And for different recipes, we learn how to measure this differently. Sometimes this summarized result doesn't do justice. So let's look at the example case. Here, this is the printed experimental image. On the left, you have AI predictions, and on the right, you see 3 color images. So dark gray means that both AI and real print has it. Blue means that only AI has it, the real image doesn't, and red means that vice versa. So this just tells us, this computed symmetric difference just tells us that this model does a great job with overall size, width, and here are where the errors. Some of the errors are related to the shrinking and some optical scale factor, but we are enhancing these models to get more and more accurate. Can we do more than just predicting the outcomes like the shapes? Can we predict resistances? Yes. So we start using this basically physics and these type of implementation that where you have process parameters and layouts, you can get the optical projection, and from having the optical projection, you can use the physics informed models to predict the shear resistance or resistivity or overall resistance of a structure. So all of these can be selected. For this, we need to add a layer of measurement where we need to measure devices automatically. If you have a flying prober, that's fantastic, but we kind of modified a semiconductor automated prober, and we learned a lot. For example, these sheets are not staying flat, especially for polymides after sintering. So we had to learn a few tricks how to get things correctly. And also we need to buy a basically largest radius of curvature probe so it doesn't poke through the cured ink. So there are a lot we learned how to navigate that sub-ideal cases. And it learns to predict the resistance pretty well. And we have a mean average error of the around half O for our prediction for different recipes. All of these results, again, I will share the publication for it at the end. All of these are available to look more. The second case or FHE implementation for using AI is to add a new type of sensor and sensorization. And here we collaborated with Cornell and the spin-off from Cornell, Giga. Giga is a company that develops these imagers. These are ultrasound imagers. They can measure density, they can measure speed of sound, but they can measure it over a very large array, 128 by 128. Each pixel is around 50 micron, but they do have a better versions. The one that we had was around 50 micron. And this is a 16,000 pixels. And they operate at very, very high speeds, high frequencies, around 2 gigahertz. Compared to the medical ultrasound, this is 100 times higher frequencies. And they can measure the differences in acoustic impedance or differences in material properties. So we designed a closed loop operation, and I'm going to show some examples of some Dragonfly printed devices that was measured, and also some Volterra measurement with extrusion printing and inkjet. And the idea is, can we use the parameters of the printed lines and printed ink and how it changes over different substrate to correct for a certain outcome and optimize a certain outcome. It could be dimensions, it could be roughnesses, it could be resistivity. So it depends on what's the outcome. A goal can be selected. Sometimes probably if there are no competing processes, multiple optimization can be put together. Here, what you are seeing is two different examples. Volterra is printing on a PCB, and Volterra is printing on a Giga chip. And let's look into that closely. On the left, you see a real-time ultrasound image when Volterra prints a silver ink on top of the imager. This work is done at Cornell and collaboration with Giga. You can directly measure the acoustic impedance. Each pixel has a value in voltage, but really shows the amplitude of the ultrasound echo that comes back reflected from the line. And you can also learn the differences between printing on silicon, which this transducer is made of, or printing on FR4, and you can learn the scale factor that you can learn it and correct it. This is work of a postdoc at Cornell, Sai, that she has pushed this to be integratable in some sort of a process flow for the Volterra. You can see there is a parameter in extrusion printing has something to do with pressure, how hard you are pushing the ink out, and with pushing it harder or softer, you can tune the amount of ink coming out, and with changing the height, combination of the pressure and the height of the nozzle to the substrate, you get a different profile. You can measure the acoustic impedance of that profile in real time, and using that, you can see different parameters will have a different impact, and over different features that scales also differently. So this type of the methods can be implemented back, and you can use it for doing some optimization again for measurement. Sometimes implementing some of this type of measurement is difficult, so it's not straightforward for every single printing possible, but also sometimes you can make a measurement after print. Here for Dragonfly inkjet printing, we were interested in creating coupons with different depths, different sizes, and different kind of configurations, and we wanted to look at the ultrasound images to characterize the acoustic impedance of different kind of implementation. So summary here is sometimes when you don't have all the signals or all the inputs, you can't use the AI and data to correct. You need to integrate the right type of sensor or right type of measurement. Maybe a few other high-level considerations that I would like to share here is virtual metrology is important because we are predicting shapes, and sometimes that's not good enough. We have to make a measurements that what's the width, what's the resistivity. So a lot of times, a lot of computer vision and image processing sometimes comes with the automated measurement tool, but a lot of times you need to write a specific codes that changes by changing the background. The way inks are drying, the way substrate changes. Sometimes this needs to be really adaptive and changes over time. We have developed a lot of kind of unintentionally, but a lot of code that helps us to deal with the prints from inkjet printer, thermal inkjet, piezo inkjet, the prints from the also different type of extrusion printer. We had a collaboration with LAM where we wanted to compare not just the feature, but entire figure. For example, if there is a CM image, how to compare it with simulation, or if there's AI predicted, how to compare it with real-time image. This was published a couple of years ago at IEEE Transaction of Semiconductor Manufacturing and ASMC. But if I wanted to put it into context of the printed electronic, we are looking at pixel-wise comparison, alignment, and also autocorrelation is being taken care of. After that, how accurate pixel-wise are the predictions are. This works slightly better for these applications. So when we are developing AI, we should think about how to validate and how to correct if there is problems within the prediction. First step is less quantitatively measure, and to measure we have looked into the spin division algorithm where help us with computing the symmetric difference or binary difference between two images. This is just a binary example, but just imagine this could have a grayscale red and grayscale blue, means that you can actually compare things in grayscale areas. Now here I wanted to also say a few things about data. AI and machine learning, specifically for cat versus dog type of problem, has been progressed very fast because data is available for FHE, for semiconductor. You can click and download the data, and that sometimes limits the progress. A lot of virtual metrology is needed. Sometimes even you have a data, you wanted to measure certain things within data. And also test automations is essential for printed electronic and implementing data. And in my talk, the focus is process development and predictive models for correcting a process. But this could have some sort of a printer maintenance or overall yield type applications that some of these models can be modified to be working there. We have done also some interesting explorations. We have integrated an acoustic emission sensor where you could actually use it for the condition monitoring type purposes. We have integrated the camera, the smallest camera that you could integrate to the directly the printhead. And also we have, as you've seen, done ultrasound-based implementation. Each one of them could be a separate talk, but we have explored some of these. Some of them really showed a value. Some of them proven that there are problems within the measurement. In terms of where AI can be used, just you can use these predictive models if they are proven to be accurate and they stay accurate given all the changes like batch-to-batch variations, drift of the machine, change of the surface of the substrate. They can be three categories of the work. Closed-loop real-time control, where you wanted to correct something in real time, but sometimes next print type measurement. So these are the type of metrology that you are making a measurement after each print and you are trying to correct something like print proximity correction. If you know what's the outcome, you can change even layout if the process parameters or the material parameters are not completely available. We can do a batch correction. So these three levels can be kept in mind for implementing the AI models. And also we can think about applying AI for different type of applications. Some of them are including different sensors and developing more accurate twins. We can use potentially these predictive models to maintain, maybe develop, but more importantly, maintain a PDK so the process does not drift. Automated testing and metrology itself has some uncertainties that developing twins for them could help understanding the underlying root causes of a problem within a print, and a lot more applications that depend on who you talk. Digital twins or twinlets or maybe multiple twins could be needed for solving a problem. I mentioned data, so very quickly on data, what I learned is nobody wants to share data, especially if it has a smallest commercial implementation. Actually, there are so many legal concerns about sharing the data. It doesn't matter how many NDAs are being signed. There are some mitigations that we have been exploring. For example, federated learning is one of them. In this type of measurement, data stays within the user. The models will be shared, and the shared weights and the models are going through number of loops to get optimization. We have been looking into this for some time. We have some implementation that now for semiconductor compares the centralized versus federated learning. We are almost lossless, means that quality of the prediction does not change. But the problem is some network setting firewalls passing through that is a little bit of a problem. Now we are working on quantification of the how much of a mistake in one of the users will affect overall quantitative prediction accuracy. So things like that are very interesting that we can use. And also just imagine ink manufacturer has a ton of data, a user has a tiny amount of data. That imbalance could bias the learning outcomes. We are exploring that, and I'm sure there will be papers coming out of our group. There are new models are out. This year we have NVIDIA Flare, actually late last year, released to the public. So this is a more interesting federated learning platform, and these will be implemented in more and more type work. This is our approach. We have upcoming paper. We have a recent paper on I shared the result, but I just wanted to say that this still does not completely answers the question that data has IP concerns. How about the learning from that data? Does the weights of model has a IP concerns? That's a good question for community that I would like to learn if still learning from a data of some specific user has IP contamination concerns with it. But in summary, we looked at the AI and digital twin for manufacturing processes. Two examples were semiconductor and inkjet process. We looked at specific DNN developed for inkjet printing using gigahertz ultrasound, and also we looked at different considerations and requirement for data and developing AI models. If I just wanted to conclude, I think AI models cannot be generalized easily. There are definitely ways, but maybe not easy. But even those locally developed for specific AIs could help with reducing time and cost of the process, help with aging and drift cases, can be repurposed for maybe maintenance of the tool, or catching problems like drifts early before something completely lost in a large batch of the processes. It could be used for accelerating process development. And just imagine if these models are 80% or 90% or better than that, but accurate, you have a chance of getting result within 90% accuracy in instance. Of course, after you train a model, it just helps with improving the overall implementation. I think that's all I wanted to say. Just upcoming workshops. We have a workshop in person in Hilton Head, but focused on MEMS manufacturing. We have also a hands-on training within FlexTech a week after. Please join if you are interested. And also, these are some of the publications from my team. I think we can open it for questions. I don't know if somebody can help me with the questions.
Yeah, Ben, I'll be happy to help you with the questions. We had a couple of them come in during the webinar that took me a few minutes to notice, and I didn't want to stop you since you already moved on. The first was, it was actually about halfway through the webinar, there was a question about the extent of AI, referred to a specific slide. So I'm not sure if we're going to be able to address that one directly, unless the speaker can, or unless the person who asked the question can maybe provide some more information on what specifically the topic was about. The other question that I think you can address is, there was a question about, you had referred to virtual metrology, and there was a question, the question was just, can you explain a little more about what exactly you mean by that, and what that encompasses?
So virtual metrology has been used as maybe two different categories, and both are relevant. One is if you have a sample, sometimes it's very hard to measure everything, and sometimes you can interpolate between the measurement points, given some understanding of the process. That basically virtual metrology helps with reducing the real metrology's time. That's one way of looking at virtual metrology. The other way is, sometimes you have a post-processing of a measurement, and these are not really for changing things like compressed sensing idea, but just extracting a feature. Those feature extractions with human in the loop, sometimes easy to make decision, but adds the bias and also makes things slow. But if you are dealing with thousands of images, makes things harder. I just want to give one number. The AI model that was predicting the SEM images, that was 32,000 images. The AI that learns to predict the printed electronic from the inkjet, that was around 16,000 images. But I just don't want to scare you. Probably we are doing overlearning, because we also did 256 image pair for plasma etch SEM. So depends on what you are doing, you might deal with a large number of data. So this virtual metrology and basically measurements that can be extracted features or can be filled for the measurement that you missed within the process, that could help a lot. I hope that answers the question, but I'm happy to follow up.
No, it definitely does. And there are, in my experience, there are a lot of parameters that we want to measure for which it requires that sort of extraction of features. And oftentimes in the past, at least, it has been very human in the loop. Things like line edge roughness and edge to edge spacing, like they're not two parallel lines. They we approximate them with parallel lines, but we need to decide exactly how we are going to measure. And that's about the simplest structure that you can imagine. If you start taking into account the 3D profile, for example, it becomes considerably more complicated, even without, complicating the actual, physical structures in any way. They are what they are, but you're just looking at additional descriptions of them, and trying to define the same parameter. I don't see any other questions in the chat or in the questions pane, but we do have a fairly good attendance. So if anyone has additional questions, please enter them. Meanwhile, I'll ask you a question. So Ben, you went through a lot of different elements there. I think ultimately, one of many destinations that people would like to get to, with all of these predictive AI models, is to take all of the process description that we're able to, or that we're able to generate, the predictions that we're able to generate, and feed that back into the design process so that we can optimize our design subject to real world manufacturing outcomes. How do you see what do you see the options we have for paths forward to be able to close that loop back into the design into the design process so that we can really accelerate, not just maybe features, but overall, say, maybe we simplify it and just say a circuit design that we want to optimize.
Sure. So here, maybe I can use just this slide. Here, these arrows in this model that you can see, the prediction of a feature going out is bidirectional because these are just weights. So we have tested different methods for cycle consistency, means these arrows goes backward. So for a one feature, you can go backward. But if we think about electrical response, for example, we have learned here, we can predict the resistance for a given process parameter. So if this resistance is a part of the circuit and you can go backward, you can put it in a netlist like a model, and you can create overall type of the assessment. One interesting consideration for digital twins and for the predictive models can be scaled from process to device and to the circuit and system level is required interoperability between these AI models and simulation tools. So existing circuit simulation tool, just imagine everything is ideal or some close to ideal that we know works. We wanted to look at one AI printed part or a couple of printed part. If that digital twin or AI model can work with a simulation tool, you can take advantage of all of those DC transient steady state analysis and whatever we do in a circuit design, plus these process induced variations or material induced variations. So interoperability is a key for connecting some of these AI models to that simulation and modeling or circuit analysis infrastructure.
Yeah, it's interesting that there may be options to either update a design based on, say, a material and a process, or options to optimize the process subject to a design and a material. And it's that will all play into how or I guess arise from how they get implemented by design and process control software in the future.
Yeah, definitely the co-design of the process and device and even circuit at different levels could happen every time there is overhead of development of these. So if there is a justification that, with a simple independent optimization, something cannot be solved, then these co-design and co-optimization of the devices and circuits can work, but it's just going to be a more development, more connecting these models together and trying to validate them, because a lot of times you need to validate what you learn is how accurate it is.
Exactly. All right. Well, I do. Oh, let's see. I do not see any additional questions. Actually, we did just get one. You mentioned many great opportunities for AI implementation in electronics manufacturing. What would you consider the low-hanging fruit in adoption at scale? It's a great question, Nick.
So the one, I think the low-hanging fruit is, again, this is my feeling. It could be incorrect. I am a little bit cautious about saying that. It seems like there is a ink kind of a batch-to-batch variations in the flexible hybrid electronic material is much more significant compared to the semiconductors. And that batch-to-batch variations, it just means that every time I get a new batch, I need to update models slightly. So for example, for a certain batch, if there was a certain recipe, can AI help me to do a first print, learn from that print, and correct things like print process proximity corrections? And I think that's the lowest hanging fruit. I just don't know enough sometimes about some of these ink characterization techniques that what we can actually measure in an ink or in a substrate to call it a certain variations. In my idea always was less print, less electrically measure, because it doesn't really matter how beautiful our circuits, the electrical response matter, and let's use that electrical response as an indication that there is a drift. Let's compensate for that. I thought that compensation could be a low-hanging fruit that, at least in my lab, we have dealt with this kind of batch-to-batch variations or aging of the ink. Sometimes it's because we are not good enough to keep it in a right kind of conditions. But that, I thought, is an interesting direction.
Yeah, that's excellent. I think it's a great topic for us to continue to explore after the webinar. We are a few minutes over time, so Ben, thank you very much for the excellent presentation. Really enjoyed it. And thank you to all of our attendees, and keep an eye out for subsequent announcements of more talks in this series. Look forward to seeing you all again in the future.
Thank you so much for having me.
Yeah, thank you. Bye.
Thank you.